So now we're going to start looking at energy with fields, and we are mainly with this chapter, remember, looking mostly at electric fields, so that's kind of what we're doing the most of here. But yeah, it's really all about energy. So potential difference is basically a way of looking at energy. So recall work done by a uniform electric field. So imagine we've got an electric field that's somewhat constant, which can happen perhaps between like parallel plates or something like that, where we look at it as if it's constant. If an electric field moves a charge a distance delta d, or I suppose you could even call that here, you could go by delta r, delta d, whatever, then the work is just whatever the force is times by delta d, which you could write as, I always want to say QED, even though it's kind of an epsilon, and if you keep doing physics, QED definitely has a different meaning, but and this here is just replacing, remember that the force, right, is just, or we defined epsilon as whatever the force is divided by Q. So if you multiply both sides by the charge, right, you can basically say the force is just the E times Q, right? So that's all that's happening there. It's just because we often like to look at the field strength or whatever and not, we don't necessarily have a charge there, then we can look at it that way. This just comes back here. Same as it was when we dealt with gravity and whatnot. But really think about what it means and try to understand it. There is a negative sign there in the equation, okay, right? So the idea is that if a system does work, so for perhaps you've got a positive charge here and a negative charge here, and you just leave it, right? So what happens? Well, the charge moves all by itself, right? I guess in this example, the positive charge is somewhat fixed, and I just let that negative charge move toward it, right? So this is work done by the system. It's done this work all on its own. One way you might think about this is, like you could say it's in a lower energy state. Once that electron, or this negative charge, whatever it happens to be, moves, right? It's done this on its own. So it doesn't have as much potential, if you will, to gain speed anymore, to gain kinetic energy somehow, right? Whereas if you go the other way, right, if I do work on this system, if I actually have, a positive and negative charge right by each other, right, and I do work on the system, so I actually take this charge and I move it over here. I physically move this charge so that it's over there, right? I've done work. I've done positive work. I've done work on this system and changed it. So that would be positive work. Whereas if now I leave that system and the thing goes back the other way on its own, we say, oh, that's negative work, right? It just, the system did this all on its own. So, but also be aware you could have the opposite case, right? If I had two positive charges, right, they want to repel. So in this case, I could actually I'd have to do positive work, would mean if I took this charge and moved it closer, now I've actually increased the energy of this system, right? So I wouldn't worry so much about the negative sign here. Just really understand that if the system is doing work on its own, that's negative, right? Whichever way, direction the particle happens to move. Whereas if you do some work on the system, that should be positive. You've added to the energy. So a simple, hopefully, example, a proton moves 0.25 meters in an electric field of magnitude 400 newtons per coulomb. Calculate the change in electric potential energy. So in this case, we're dealing with a constant field. So you could sort of look at this, electric field. We can kind of look at that and just say, well, look at this like it's just sort of in this direction or whatever. We've just sort of got this constant electric field. This could, again, perhaps between some parallel plates or something like that. And we've got a proton that moves 0.25 meters. So maybe we've got our proton starts out here. And we can call this point A. And then it moves to point B, which we know is 0.25 meters. So we want to know what's the change in electric potential energy, right? So how much energy has this particle essentially lost as part of this system? Or maybe I'll try to use a capital E. Try not to confuse this with elastic potential energy. But in this case, delta E as well. We got the equation right up there still, so minus Q E delta D. So pretty much just plug in the numbers. The charge on a proton, the negative is 1.6, I guess 1.602 times by 10 to the negative 19. The electric field we're given, that's just 400. And delta D is 0.25. Multiply those together, we get, well, 400 times 0.25 is just 100. So that's 10 to the negative 17. All right, so that's delta E, right? We're saying this is now, so this is an energy loss, essentially, right? This system has done work on this particle. It's now, in a sense, in a lower energy state, so anything it does like that on its own, we can look at it that way. All right, electric potential, or voltage, if you will, V, but often just called like electric potential. The electric potential at any point in space is the energy required to move a 1 Coulomb charge from infinity, or hypothetically really, really far away, to that point. Okay. So two things going on here. One, this is kind of similar to gravity in that sense that we looked at, we said the value was 0 really, really, really far away. So we're sort of drawing on that, which you could say, you could define energy that way too. And also it's per charge. And we didn't really have an equivalent for that, right? So far, we really have, remember when earlier we looked at forces, right? So we had the electric force, and then we had the electric force per charge, which we said, okay, that's just the electric field strength. Now we've got the electric energy, which we just looked at, and now we've got the electric energy per charge, right, which we're using V. If you look at like gravity that way, right, and you say we had the same thing, we had, if this was a G, right, we had the force of gravity. Here we would have had, the equivalent would have been G, right, that was sort of the force per kilogram. We had energy, right, we had EG, right, the energy in a field, but we didn't have anything like this. We never looked at the energy per kilogram or anything like that. So this is a really new concept in that way, but it is just really just energy per Coulomb, right? So if we look at that, there it is, just written in as sort of an equation, V, right, just E per Coulomb. Or since we just said that the energy here, right, was essentially like QED or whatever, so you just divide by Q or work that out. So it's just whatever the electric potential is times by whatever distance it is from the charge. I would highlight that, right, the units, joules per Coulomb, or volts. So whenever you think of that, when we're talking about voltage or whatever, just remember it's essentially energy, right? It's just energy per Coulomb or per charge. So we're just not dealing with any specific charge or the fact that there's a particle there, but are saying if there was a positive 1 charge there, that's the energy that it would experience. Or rather, we can look at electric potential difference, delta V. And so rather than just considering V from infinitely far away to some point, we often want to just look at delta V, or what is the change. So if you did have, let's suppose we got some charge here. I'll make it big. So I've got some big charge here. It's positive, so if I wanted to, I could draw all the lines. Right? This would represent the electric field lines from this charge. Everything would want to move away. So maybe I've got some hypothetical point here, or I've got some. So remember, if we're dealing with potential difference, we're dealing with this sort of hypothetical, right? Here's my right. We're kind of dealing with that, and so maybe this is at some point A, and then I could have some other point here B, right? And so maybe that way I could actually consider what is, right, delta V from A to B. Might be something that I want to look at here or whatever, right? And that would just be EE over Q, which in our case is just and if we use this, I always feel like this is kind of a neat thing to sort of point out. One way to think of electric field, because we're already using it. So this is kind of the first way to look at the electric field strength at a point in space. Right, we already did this earlier. We looked at it and said, well, this is basically the force that a positive 1 Coulomb charge would experience at that point. And the units work out, right? It's newtons per Coulomb. So this is a force. We could look at it that way. But now we could also look at it a different way. We could look at it as the electric field strength at a point is how much energy a plus 1 Coulomb charge would gain or lose if it moved 1 meter, right? And that way, and that's also consistent with the units here, right? You could look at this as volts per meter. So depending on the question, or depending on what you're thinking about, it could be helpful to kind of think of it this way, or to think of electric field as this is the amount of energy that a 1 Coulomb charge would gain or lose if it moved from one point to the other. Helpful for concept questions and stuff, I think. Okay, I have one slightly more involved question where we're kind of going to use this, and it goes all the way back to kinematics and everything. So here we've got an electron and enters a parallel plate capacitor with a speed of 6 times 10 to the 6 meters per second. Pretty fast, but for an electron, I suppose that's the typical speed. The electric field of the capacitor deflects the electron 0.618 centimeters, and that's actually shown down here in the diagram, so you can sort of see the path of the electron at the point where it exits. Find the magnitude of the electric field in the capacitor and the speed, or I guess probably should have said velocity there, but the electron when it exits the capacitor. Yeah. So we're saying there is some electric field in here, we just don't know what it is, right? I suppose if we could have some sort of coordinate system here if we wanted. The electron's moving that way, so let's just say this is the positive x direction, and why not make that the positive y direction? That is the direction it actually deflects. And just like with dynamics, or like energy, I suppose in some cases, we can look at each direction independently. Right? And note that initially it's got a velocity that is purely in the x direction, and there's no force in the x direction, or practically speaking, there's no force in the x direction at all. So that component of the velocity should remain constant. What's going to happen though is it's going to be accelerated in the y direction. Now this particle, it's going down, it's going toward the positive. Yeah, so, well, it's an electron, so it's negatively charged, so that kind of makes sense. Now this stuff is in centimeters, so the only thing I guess I got to be a little bit careful with when putting this stuff in. If it's 2.25 centimeters, right, it's 0.0225 meters. So we want to just be consistent. These equations are sort of made, and the constants are made to have everything in SI units. So the first thing, just sort of like with gravity, if I'm looking at this like a projectile or whatever, right? Well, I need to know the force, right? If I'm going to get the electric field, I need the force. In order to do that, right? I know force is ma, right? F equals ma. So I need the acceleration of this thing in the y direction. So I can sort of, but also, I'm not told the time, right? But I do know this. I do know the speed in the x direction. So vx, let's say, this is constant, and this is 6 times 10 to the 6 meters per second. And so I could figure out the time, since I know the distance it travels in the x direction. So time just equals distance over speed. So in this case, it's that. And I get an itty bitty number, 3.75 times by 10 to the negative 9 seconds. So almost 4 nanoseconds this thing takes to go through here. Now I can look at the y direction. And this kind of becomes like a dynamics problem, right? Where I'm just looking at the direction something's falling or whatever, right? So I know the time. I just found that. Time. I know V1 in the y direction is 0, right? It doesn't have any there at all. I know the distance that it travels is given to me right here, so I know d in the y is 0.00618 meters. So what would I want? The acceleration really is the thing I want. And that means the equation that I would want would be d equals v1t plus 1/2 a t squared. Put in those numbers. Well, this here is 0 because v1 is 0. And so that means 0.00618 equals 1/2 a and 3.75 times 10 to the negative 9 squared. Multiply both sides by 2 and divide both sides by 3.75 times 10 to the negative 9 squared. And that should tell us that A equals 8.79 times 10 to the 14 meters per second squared, which is decent. Then I can use the fact that, so the electric force in this case is just ma, which means QE equals ma. Thus, the electric field, which is one of the things I want, equals ma over q. The mass of an electron, if you haven't memorized it, is 9.11 times 10 to the negative 31. not very massive at all. The acceleration I just found, 8.79 times 10 to the 14. And the charge on an electron, 1.602, or just 1.6 if you want, times 10 to the negative 19. Which means the electric field here is 5.00 times 10 to the 3. Newtons per coulomb. Just putting the numbers into a calculator. The other thing, which I sort of skipped here, I guess if I want the final velocity of this thing, that's back to just basically dynamics, right? I know right? I know V, let me try to draw this thing here. Suppose the final velocity is something like that. And so this is Vx, which is constant, and this here is V2y, which I didn't actually solve for. I found the acceleration, I found whatever, so in this case V2y would be, I could just use the equation, what, V1y, which is 0 plus AT. And the acceleration I already found, 8.79. And the time was 3.75 times by 10 to the negative 9. Uh, 3.296. And V1, did I draw that very well? V1x is constant. That's 6 times 10 to the 6. This is 3 times 10 to the 6, so it's basically half of it. So I might have angled this a little bit more, but that should be okay. And we've done this process lots of times. We can say V final is just going to be the square root of both components. Let me just write that was 6. 6 times 10 to the 6 squared plus 3.296. So the actual V is 6.846. And it did actually say speed in the thing, but if I wanted to, I could also find theta in this case would just be the inverse tangent of, let's do y over x, so which I get 28.8. So then I can say, therefore, V final is 6.85, let's say, times 10 to the 6 meters per second. I'll say 28.8 degrees down from the horizontal, at least the way it's drawn. Because why not go all the way and get the actual velocity?